Thank you, Mr. Troshenko. Now I would like to ask Vladica Nikolic to present us a paper titled The Effect of Heat Treatments on the Microstructure and Fracture Toughness Properties of Drawn Tungsten Wires.
Okay. So, good afternoon, everyone. Okay, now we hear. Good afternoon, everyone. Thank you for the introduction. So today I will tell you about the work that was done at the Eric Schmidt Institute of the Austrian Academy of Sciences regarding the microstructural and fracture characterization of tungsten wires. And here in this talk I will focus on the influence of heat treatments on these properties. So as a starting point, as underlying motivation of the work, we come to the story of nuclear fusion. Here you can see currently under construction reactor ITER that will be in a few years, hopefully the largest one ever built. And on the side you can see the cross-section of a vacuum vessel. When we think of using materials for such an application, to say the least, the environment of a reactor is very harsh, very hostile, and it is not a very easy task to deliver appropriate materials. In particular, this part, called the diverter, will be the component of a reactor which will be heavily exposed to heat and radiation and is one of the most critical parts. And this is where tungsten comes in the picture. So tungsten, due to many good high temperature properties, was chosen as a main diverter and plasma phasing component. So the list of good things is endless, to say, but when thinking of using tungsten as a structural component, there is a very large problem, being that it is a very brittle material. And over, well, decades, and in particular last several years, there was a lot of research focused on this issue, and many toughening strategies are being investigated to overcome this problem. One of them is building a composite material, tungsten fiber reinforced composite, where the wires from my title come in the picture. So essentially we take the commercially available fibers, and they are embedded in a tungsten matrix which is produced by a CVD process, and in such a way we actually can obtain some better toughness results and better ductility. So as a main reinforcement of such a material, we have the fibers or the wires, and as the whole structural integrity depends on their properties, it is very important to exactly know how they behave in fracture regard, and also microstructural stability is a very important issue. And when thinking of using tungsten in a fusion application, these two things define the temperature limit of use. So the DBTT, which unfortunately with tungsten is rather high, defines the lower limit of use, and the recrystallization temperature defines the higher limit. So it is very important to know exactly where these temperatures are and to try to expand this limit if possible. Okay, so we were investigating two types of wires, namely pure and potassium doped wire. Diameter was 150 microns. And as the first part was, of course, microstructural characterization. And these materials, during the production, they experience a very high degree of deformation, which has very large influence on the resulting microstructure. In this case, we have something that is called bundle of fibers microstructure, meaning that it is a very elongated grain structure along the drawing axis. And the whole microstructural characterization was done in two views. So we were looking at the longitudinal section and the cross sections to get a complete picture of the microstructure. Analysis was done in relation to different heat treatments. Here you can see the temperature range with the highest temperature of 1600 degrees C that was done. And then all the fracture properties were done at room temperature with 2 chosen annealing treatments as an addition. So with the microstructure, as I said, it is fibrous elongated microstructure. Here, hopefully, you see these elongated very thin grains. And if we look at the cross-section, in magnified picture it's seen better, the grains are curled, again as a result of deformation process during production, and they form these ribbon-shaped kind of structures, also known as Van Gogh sky structures. So the microstructural evolution as a function of annealing was mostly characterized by EBSD tool, and here we can see that evolution. So the top pictures are corresponding the pure tungsten, and here we have the potassium doped tungsten. This is the cross-section. And if we follow the increase of annealing temperature, we can see that in case of undoped material, there are large differences in microstructure upon annealing. So significant grain coarsening can be observed, and also if you look at the graph, we can quantify this. So we can determine the diameter of the grains and see by which extent it increases at the highest annealing temperature. In the case of potassium doped, there is slight increase, but uncomparable to the undoped material. The very green color is an indication of a very strong texture. This is something, again, as a result of deformation during the production. It is so-called Fibertech with a very pronounced 110 direction, and when looking at different annealing states, we can see that this texture is preserved through various heat treatments. And now let's look at the longitudinal section, so from the side of the wire. And here we can see these elongated grains again, and again the same comparison is done. So for the pure tungsten, already an intermediate temperature range, we can see quite extensive changes in the grain morphology, and upon highest annealing treatment, there is complete loss in elongated grain structure. They change to round, quite global, large grains. In contrast to that, potassium doped one, again, quite stable. Some grain width increases a bit above 1400 degrees C, but nevertheless, the elongated structure is still preserved in this case. And here, accordingly, we can see the changes in grain length and width. And then 2 additional pieces of information we collected. One was analyzing the grain boundaries. So here you can see grain boundary map in cross-section, longitudinal sections. And here we wanted to look how, of course, the amount or total length of grain boundaries, how it decreases with annealing temperature, but also to look into the nature of grain boundaries, so whether they are low-angle or high-angle grain boundaries, and the number fraction in each annealing treatment, how it changes over all the various annealing states. And all of these complements gives us information that complements the discussion about different annealing phenomena that take place. And final information that we obtained regarding the microstructural stability was hardness measurements, where we can also see the softening effect pretty pronounced for pure tungsten and not as pronounced as potassium doped one, and we could even correlate with linear relationship the information regarding the hardness and the grain size in this plot. Okay, so to somewhat summarize this part, we can say that pure tungsten already at lower annealing temperatures undergoes recovery process, and that after or in the range between 1300 and 1400 degrees C, it is fully recrystallized. In contrast, potassium doped one is significantly more stable. There are some milder microstructural changes, but the almost the same microstructure is preserved even at high annealing, and this is all due to the dispersed second phase being the potassium. And here you can see these small dots and at various places. The potassium is organized in rows in this case, and it is situated at the grain boundary exactly. So it has an effect of pinning of the grain boundary, and in such way it inhibits their movement and shifts the recrystallization temperature to higher temperatures, which is, of course, when we go back and think about fusion properties, a very important point. And then selection of our fracture samples was done. So we wanted to look at fracture properties in the as received state, and 1300 and 1600 degrees C were chosen as two additional samples. Fracture experiments were done on a Kamrat and Weiss micrometer scale tensile device. Single edge notch tensile specimens were tested. Here you can see a little sketch. And the pre-crack that we need to insert was done by femtosecond laser. And what did we get? Okay, so first the results of as received state of the material. So everything is, again, a room temperature study. Here, if we look into the value of fracture toughness, we see quite a large scatter of data, in the sense that the obtained results are in the range from about 25 to about 40 megapascals per square root of meter, which corresponds to occurrence of both the brittle and the ductile sample behavior. So essentially, some samples failed brittle, some samples failed ductile. And this is a strong indication that DBTT is happening at this range. So it's about, we can say it's about room temperature, which was our testing temperature. And that's first important aspect that we can see. And second very important aspect, in both of the cases, both ductile or brittle appearance, there is a very large crack deflection happening at the beginning of the fracture process, which you can see nicely, well, in both of them, as this step. So we want designated mode 1, which we want to accomplish, is not really happening. So at the beginning, the crack deviates, and it takes the path of along the grain boundaries, along these elongated grains, which is a direct indication that we have a very strong anisotropy of our fracture properties. And brittle behavior, in this case, is characterized by transcrystalline cleavage, and in this case we have a so-called knife edge necking of the grains, which, you see by these, again, like curled structures. I have time?
3 more minutes.
Okay. So going now to the next set of samples, 1300 degrees C annealed samples. Looking at the toughness values, we can see that there is a decrease in toughness, with an effect being very pronounced for pure tungsten. So there is embrittlement by annealing, essentially. And if we now look at the fracture surfaces, so left is potassium doped one, we see very similar appearance as in the case of as received material. In some areas, there are roughly flat cleaved grains, but these areas, as you can see in this overall fracture surface, they're very small. So we can consider this predominantly a ductile failure mode. And now if you look at the pure tungsten, we see a completely different picture after annealing. So here there is no crack deflection at all. So our initial direction of the crack propagation is preserved. So it just goes through our wire. And in this case we have transcrystalline cleavage again, but there are also some intercrystalline areas as well. And now if we go to 1600 degrees C, toughness decreases even more. In the case of the doped material, these areas of cleaved grains, so brittle areas, increased in their size. And for the pure one, we see a pretty similar picture with with an increase of this intercrystalline failure mode, which is somewhat localized at the edge of the wire, which was also anticipated to some extent from this overview EBSD scanning across the entire cross-section. So here we see the entire wire. And we noticed before that there is some localized variation in crystallographic orientation. So it was somewhat anticipated. Okay, so to sum up, essentially the three main points is that these kind of materials have very unique microstructure as from the production, right? So high degree of deformation results in this elongated structure. And if we submit it to various heat treatments, substantial changes occur in the case of pure tungsten. And we also could see that this is successfully shifted to higher temperatures in the case of doping, so the doped material. And a very important aspect, and the most important aspect, is that microstructure, at least for tungsten, is severely controlling the fracture process. So it's very influential. And we could directly see that from the observed appearance of the microstructure at particular temperatures, which then resulted in one of 4 appearing failure modes.
Thank you very much, Ms. Nikolic, for a very interesting presentation.